Throughout this class about Earth's landforms and the processes that make them, we'll be discussing different rock types. In other words, the conversation will include different minerals and rock types. So the purpose of this presentation is to give you that background information you'll need for the rest of the course. This presentation starts with an understanding of the basic composition of the continental crust, and then you'll come to understand why that composition generates different types of minerals, an introduction to different rock types, a little bit of detail on igneous, sedimentary, and metamorphic rocks, and lastly trying to get you into the mindset of how geologists think about rocks and the time scale involved in making and eroding rocks. If you're looking for additional background information on rock types, please go to this website, register, it's free, and you can obtain additional information about sedimentary and metamorphic rocks. Also at this website, there's supplementary information you can obtain on geologic time, evolution, basic minerals, volcanism, and igneous rock types. All of these are excellent presentations. Our crust is composed of 3/4 oxygen and silicon. So it would make sense that most of the minerals would have oxygen and silicon in them. Aluminum, being the third most important element, often recombines with oxygen and silicon. Iron is substantial, and then you have a set of four elements, calcium, sodium, potassium, and magnesium, that are all in 2 to 4% range, that provide the nutrients that we need for life and the vegetation needs to grow. You might be amused that in a typical lifetime you'll consume these different sorts of earth materials. Minerals are naturally occurring substances with a very specific chemical and crystalline structure, and rocks are when you combine a whole bunch of minerals and different rocks all together. Sand, quartz, rock salt, halite, iron ore, hematite are all examples of minerals. In contrast, there are different materials that are not minerals, that do not have a regular crystalline structure. Here are a few examples of minerals that I'll discuss in the context of different lectures. Silicates are minerals that have silicon as a base and oxygen. Quartz is an example of a very common silicate mineral. Another example of a very common silicate mineral would be a feldspar. So feldspars have both silica and aluminum, and then when you add in an extra cation, a positively charged ion, a calcium, a potassium, a sodium, you get different types of feldspars. These minerals, quartz and the different feldspars, typically solidify from molten magma, making up different parts of igneous rocks. There are also minerals that result from the decay of other minerals, and that would be clay minerals. Clay minerals are extremely important in this class in that they absorb a lot of water, and they're important in soils and topics like landsliding. So clay minerals that you would encounter would be those types of minerals that stick to your boot. They have a layered structure. Arizona is a state famous for its minerals. There are several books on gems and minerals of Arizona where you can go to collect fossils. Here are some examples of, since Arizona is a copper state, a copper with cuprite, which is a copper oxide from Pinal County, and then a beautiful green malachite, and also azurite. Both are copper carbonates from Bisbee. Minerals are pretty cool, and Arizona is a great place to explore and collect minerals. The three basic rock types are igneous, formed from the solidification of molten magma; sedimentary rock, made from pieces of other rock that come to settle, or material that is drawn out of water and deposited from a solution. That would be detrital and chemical sedimentary rocks, or metamorphic rocks that are made by the reforming of minerals when they fuse together with heat, pressure, fluid, and time. All these different types of rocks I'll explore in greater detail next. Igneous are rocks that are solidified from molten magma. Sedimentary rocks are those that are deposited and buried close to Earth's surface, deposited in layers called strata. Metamorphic rocks are those that are changed. They may start out as igneous, sedimentary, or as metamorphic, and they're cooked, or they're pressurized, or strange fluids move through them and alter. Rocks can have a wide assortment of minerals inside of them. Virtually any combination will get you a rock. From a pure spatial perspective, sedimentary rocks make up the most common type of rock you'd find at or near the Earth's surface. However, when you end up looking at the depth of Earth, most of the rocks inside the Earth are igneous and metamorphic rocks, and they make up most of the crustal volume. There are whole courses devoted simply to igneous rocks and how the minerals are made. At a very simplistic levels, all that's relevant here is that the minerals are crystallizing from a melt of hot magma. The temperatures are extremely high, and that the crystal size tells you how long the magma had to cool. Very big crystals occur when the cooling is extremely slow, over thousands and millions of years. And small crystals occur when the cooling is very rapid, when the magma erupts at or near the Earth's surface. Two of the more common types of rocks we find in Arizona are basalt, that would be a lava that would be extruded at the surface, or granite, a lava that would solidify at great depth, hence the mineral sizes are larger. This diagram shows the concept of hot magma that solidifies in a large magma body over a long period of time, and hence crystals cool, and so you get an intrusive rock formed at great depth. In the same diagram, one might see the lava moving up at the surface as a lava flow, with an example being basalt. There are two general ways of organizing and naming igneous rocks. Let's take a look at the top part of this diagram, intrusive and extrusive rocks. Intrusive are those that form at great depth, have large crystal sizes. Extrusive are those that erupt at the surface, and sometimes the eruption is so fast that you don't even get minerals forming, but you get a glass like obsidian. Now, a second way of organizing igneous rocks is by their chemistry, by what they're made up of. And so the lighter colored rocks are at the felsic end. Felsic means lighter colored. Mafic means darker colored. So granite is a felsic rock that's formed at great depth, and that has the same chemistry, same minerals as rhyolite that erupts at the surface. Gabbro is at the far mafic end. It's a very dark rock, and it has the same minerals as basalt that erupts at the surface. It's just that one forms at great depth and has large crystal sizes, gabbro, and the other has small crystal sizes because it cools very fast at the surface. So as you move from mafic, less silicon, more iron and magnesium, to felsic on the right-hand side, more aluminum and silicon, more quartz, you change the color from mafic being dark and felsic being light. And although these images show intrusive igneous rocks, the same color change occurs for the extrusive igneous rocks. Click on the two different links, and Poi Hoi, to see short clips about these very different types of basalt flow textures that are actually the exact same rock chemistry. So to review again, intrusive igneous rocks are those that solidify deep beneath the Earth's surface. They have large crystals because they cool slowly, and granite is a typical example found in Arizona. Although the magma solidifies at great depth, we see granite exposed at the surface when the surrounding rock has eroded away. This is a view of a mountain in Nepal, where you can see a cross-section of the mountain. The lighter colored material is a pluton, or the magma chamber of an intrusive igneous rock type called granodiorite. And that pluton is what normally forms at depth, where finally, after millions of years, the erosion of the overlying material brings granite up to the surface where we can see it. This is an aerial view of a mountain chain in California, the Sierra Nevada, composed of almost entirely combinations of granite magma chambers called plutons. The whole mountain range at its core is called a batholith. A batholith is a combination of a whole bunch of individual magma chambers. And what you see here in this photograph is the last bit of remnant of the overlying rock. So literally miles of rock had been eroded away of the overlying rock to expose the lighter colored granite that now makes up the core of the entire mountain range. So to review, the extrusive igneous rocks are those that have the same chemistry, same minerals as the intrusive rocks. They just erupt at the surface. Because they erupt at the surface, they cool quickly, and because they cool quickly, they have minerals that are incredibly small. Sometimes in an extrusive igneous rock, you'll actually see some larger minerals. This is a rock that was trying to become an intrusive igneous rock, so some of the minerals solidified slowly at great depth, and then the magma moved quickly up to the surface, so you have a few large crystals that had already formed at great depth, where most of the rock solidified very quickly, and so you have minerals that you can't even see with the naked eye. Geologists like to look at the texture of the rock. So here are some different textures that you can find in different types of intrusive and extrusive igneous rocks. For volcanic eruptions, you might have pyroclasts, or little pieces that are blown out of the volcano. Ash or pumice would be examples. For extrusive igneous rock, the texture would be really small minerals for most of the case, because it cools rapidly at the Earth's surface. For the intrusive igneous rocks, the texture would have very large crystals, because the cooling occurs at great depth and very slowly. And you can have a mineral texture called a porphyry, where it started out as an intrusive igneous rock, so you have a few big minerals, and then it erupted, and it became mostly an extrusive igneous rock, where most of the small minerals can't even be seen with the naked eye. Pyroclast, crystals too small to see with the naked eye, crystals you see with the naked eye, and a mixture are examples of how the texture can give you clues to analyze how the rock formed. This lecture is quite long, hence I break it into two different pieces. All the material up until this point goes into the first quiz on the Earth Materials lecture. So you can go ahead and log into the LMS and take the first quiz at this point. Then what follows after this in the presentation is for the second quiz on the Earth Materials lecture. Sedimentary rocks are characterized by being deposited in layers. The layers are called strata. The rocks deposited in layers may be little particles. That's called clasts. Clast just means little pieces, and can be everything from cobbles to sand to clay. Or in some cases, in a lake or an ocean, you can precipitate the minerals like a limestone, and the mineral precipitates will fall out in layers. What's important is that all of the sedimentary rocks initially derive from the decay, or what's called the weathering, of some of the rock type. It could be an igneous, a metamorphic, or another sedimentary rock. It's just pieces break off, and pieces or the dissolved load are deposited in layers or strata. As you might expect, sedimentary rocks require some place to deposit the material, so these would be in basins. You wouldn't expect to find large basins in an area of plate tectonic collision, but in the trailing or the passive margin of a tectonic plate. So everything starts with the decay of rock, weathering, and the erosion, the movement of rock from mountains. Then the material is transported, typically by water. And then the transported material is deposited as strata in layers. The layers may be made up of pieces or clastic materials, or chemical deposits such as salt or limestone. After the pieces are deposited, they lithify. Lithify is a general word for turning into rock. The process typically involves compaction, where the pore spaces or the air spaces are squished out, and then the grains cement together and harden. The classic sedimentary rocks are organized by the size. If the size is clay and it's compressed, it goes by the name shale. If the size of the original pieces would be sand, it's called sandstone. If the size of the original pieces are pebbles and cobbles, there are two different names. If the pebbles and cobbles are rounded, as in from river action, it's called a conglomerate. If the pebbles and cobbles are not rounded, such as they were deposited in a mud flow or a landslide, it's called breccia because the pieces are angular. Breccia or conglomerate, the large end, shale, the small end, and sand, the middle end of sand. Other views of conglomerate: sand coming from sandstone and shale coming from mud or clay. Please pause the presentation and read this short excerpt from The Onion. I think you might enjoy it. If you don't know, The Onion is a classic spoof newspaper put out by the University of Wisconsin students. The sorts of minerals that you typically find in sedimentary rocks are a bit different than in igneous rocks because they're the result of weathering. The igneous and metamorphic rocks will weather and decay, and so the types of minerals you find in sedimentary rocks are those that are either resistant to weathering, such as quartz, or those that are extremely common, such as feldspars, or those that are the actual product of the decay of the original igneous minerals, such as clay minerals. Each one of these topics, 4, 5, and 6, are several courses in a geology curriculum. Metamorphic petrology, how metamorphic rocks are made, is extraordinarily complicated, so this is very simplified. Metamorphism is just heat, pressure, and fluid moving through an original rock that changes its composition, its mineralogy, its texture. So there's a gazillion different ways that you can alter and squish rocks. Generally, these different types of processes are broken into regional metamorphism and contact metamorphism. Regional metamorphism is something that you'd find with the collision of tectonic plates. High pressures, temperatures from squishing plates together will realign the minerals and make new types of rocks. Contact metamorphism would occur, say, when an igneous magma body is moving in and touching the surrounding rock. It'll cook it. And so right next to the intrusive igneous rock, you'll get contact metamorphism from the exchange of fluids and from the additional heat. This diagram illustrates the types of rocks one finds at a convergent plate boundary. In each one of these cases, the individual rocks, notice that the pictures of the minerals is that they're aligned, that the squishing process has tended to both alter the minerals and align them on a scale of your fist. This alignment is called foliation. So the most simple type of textural understanding of metamorphic rocks is to say those that are aligned or layered are foliated, and that's an indication of some sort of shearing or stress during deformation. Non-foliated metamorphic rocks are those where the mineral alignment didn't have a stress field on it to pressurize them and reforce them to form. Marble would be another example of a non-foliated. So the most typical examples one would find of foliated and non-foliated minerals would be, say, limestone turning into marble, not aligned, and granite with a combination of heat and pressure turning into a rock called gneiss. This is another graphic illustrating how a common rock like igneous rocks can be realigned by pressure and heat so that the mafic minerals, the dark ones, and the felsic minerals, the quartz and feldspars, the light minerals, realign into this cool banding known as gneiss. If you click on the link, you'll be able to see an animation showing mineral realignment into foliations. If you're from metropolitan Phoenix, or if you visited it, the Phoenix Mountains have great examples of schist all over them, which is a foliated metamorphic rock. Very common in hiking trails like at Piestewa Peak. Here are some other examples of foliated metamorphic rock. The upper image is of slate that I took in Kentucky, and the lower image is some schist from the Phoenix Mountains here in Arizona. The sorts of minerals one finds in a metamorphic rock are those that form when you heat and you repressurize minerals. They're different from the original igneous melt, and they're certainly different from the sedimentary rocks that result from the decay and weathering of the original minerals. So you get all sorts of fun minerals, common ones like quartz and feldspar and mica, and you also get ones that are characteristic of the metamorphic process like garnet. In review, the igneous rocks on the right are broken down into intrusive, formed at great depth, extrusive, formed at the surface. Metamorphic rocks are typically broken down into foliated, where the minerals are aligned, and non-foliated, where the minerals are not. And sedimentary rocks, where the layers or the strata are composed of pieces, or clastic sedimentary rock, are those that are composed of the precipitation from solution, such as limestone.
Geologists think differently than other human beings. They think often in terms of sequences of events. So if you click on the link, you'll see an animation of how geologists look at relative events and reconstruct what came first and second in order to create the geological materials that you see today. And also, you might want to pause the presentation and enjoy this XKCD cartoon that I think captures how a geologist thinks about time and rock.
I think you might appreciate this cartoon about what a geologist's library looks like, especially after you've looked at the animations and the links on the previous slide. Can you puzzle out what came first and what came second? It's a kid in a candy shop to take him to a place like the Grand Canyon, where they'll start at the top and say that has to be the youngest because it formed on top of what was directly underneath. So at the Grand Canyon, the Kaibab would be the last to form, and you drop all the way down towards the Cambrian, the Tapete sandstone. And then the geologist would notice a great unconformity, or a breaking of the sequence of rock formation, where what came before was eroded away and tilted and altered. So that great unconformity is very famous in the Grand Canyon because it indicates a tremendous gap in time, where the rock before had to be altered and folded and then eroded and then dropped down to the point where the Cambrian deposits could be laid down on top of it. So this what came first, what came next, what happened between, get pretty complicated. For example, geologists love things called disconformities. This is where you can still see one layer is directly on top of another, but there's some evidence that there was a time difference, that there was a period when deposition stopped and then it picked up again, even though it was just one layer on top of another. So this type of unraveling temporal mysteries is what geologists love. It's how they think. And you can see the great unconformity in this image, where there's a great time difference between the sediments below the double arrow, where they were laid down and they were twisted and then they were eroded, and the material that was deposited directly on top of this unconformity, or an old surface of erosion. Geologists also like to think in terms of the rock cycle. The rock cycle is like the hydrologic cycle. It's very simply the raw materials can be recirculated in a whole bunch of different processes. In this particular example, you might have minerals that form from a melt in an intrusive igneous body under a mountain range. And then tectonic pressure might build the mountain that was uplifted. And when these rocks are then exposed, they're weathered or decayed. After they're decayed, they're eroded and then transported, and then they're deposited in sedimentary rocks. Then they're buried, and they're hardened, and then they might be metamorphosed, and then they might be melted all over again. It's just the idea you can start the cycle anywhere and finish it anywhere.
The age of the Earth was discovered by geologists using the radioactive decay of different elements found in old rocks. So if you click on the link, you can see a presentation about how geologists figured out how old the Earth is.
Here are two cartoons for you to enjoy reading from the XKCD comic. It's only been in the last few decades where geologists have been able to measure the age of rocks and minerals by using isotopes that are very long-lived, that exist in minerals, that exist inside rocks. And some of these very long-lived isotopes have revealed that the oldest rocks on Earth are almost 4 billion years old, 3.8 to 3.9 billion years old, and that some rocks that are sedimentary include the individual minerals that are as old as 4.2 billion years old. These are very rare occurrences, but they've been scattered in different places in North America, Greenland, Australia, Africa, and Asia. So Earth itself is at least 4.2 billion years old and probably 4.5 billion years old. But what did geologists do before the invention of radiometric dating of rocks, they had a relative time scale that they called geologic time. And geologic time is measured by the evolutionary events in different sedimentary deposits. So the Paleozoic era would be the time of early life, such as fish, shellfish, amphibians. The Mesozoic had the dinosaurs in it, the Cenozoic being the time of mammals. And then we split out each of these eras into specific periods, where the periods differentiate subtleties in life. So the geologic time scale represented by evolution is the way geologists think. If you're planning to be a teacher, you may enjoy this particular lesson on how to use toilet paper in your classroom to grasp the depth of time involved in Earth history.
This ends the material for the second quiz. So the second half of the Earth Materials lecture, go ahead and take the Earth Materials Quiz 2 now.